Pulse Talk, bringing insights into health and wellness with your hosts, Christine and Alex.
Have you ever been in that really awful situation? Maybe your child's got a high fever, or perhaps it's an elderly parent dealing with some really persistent pain. You give them a painkiller, something you trust, maybe something that works fine for you. But for them, it's like nothing happens. Or even worse, they have some kind of unexpected reaction, and you're just watching them, still in pain. It's just agonizing, isn't it? That feeling of helplessness when someone you love is suffering and the medicine just isn't doing its job. So today, we're doing a deep dive into exactly that. Why do painkillers seem to work so differently for different people? What's really going on? We're going to explore the science of pharmacogenomics. Let's call it PGX for short. It's this pretty cutting-edge field that looks at how your specific genes shape how your body handles medicines. Think of it as trying to understand why getting pain relief can sometimes feel so hit or miss, and maybe find ways to make better choices, especially for our families.
You've really touched on something incredibly common there. Things like paracetamol, ibuprofen, even codeine. They're in almost every home. We reach for them for headaches, fevers, aches, pains, all sorts of things. But just like you said, the results can be, well, all over the map, even within the same family sometimes.
It really is baffling. Like, one person takes an ibuprofen and feels better pretty quickly, almost like magic. Then someone else, maybe your partner or your parent, takes the exact same pill, same dose, and gets, well, barely any relief at all. And then there's that smaller group who actually feel worse, maybe get stomach upset or something more serious. It makes you wonder, especially when it's your own child who's not getting relief. Feels like rolling the dice.
It absolutely can feel that way. And, that unpredictability isn't just random chance. It really points towards a kind of hidden factor. And that factor is our genetics. These tiny differences in our DNA code are actually giving our bodies different instructions for how to process these drugs. That's what leads to those varied responses. It's unseen, but really quite powerful.
Okay, so let's unpack that a bit, the genetic differences. Because it sounds complicated, but maybe the basic process isn't. Like, when we take a pill, what actually happens? What's the journey that medicine takes inside us?
Right. So any drug you take essentially goes through four main steps. Think of it as a journey. First is absorption. That's just getting the drug into your bloodstream from, your stomach or wherever. Then there's distribution, how it travels around your body to where it needs to work. After that comes metabolism. This one's really key. It's how your body chemically changes the drug, maybe to activate it or to break it down so you can get rid of it. And the last step is excretion, basically, how your body clears the drug out, usually through urine or feces.
Okay, so absorption, distribution, metabolism, excretion. A four-step process. And our genes are kind of the directors of this whole show.
That's a great way to put it, yeah. Specific genes hold the instructions for building the proteins, especially enzymes and receptors, that manage each of these steps. And just like genes determine eye color or height, slight variations mean the instructions for handling medicines can be different too, which brings us back to that difficult situation. What if those different instructions mean a common painkiller doesn't work for your child, or causes a problem for your parent?
This is where it gets really practical, I think. Especially when you're desperately trying to help someone you care about feel better. Let's maybe take codeine as an example. Lots of people use painkillers with codeine.
Perfect example. Codeine's effectiveness really depends heavily on one specific enzyme called CYP2D6. You need this enzyme to convert codeine into morphine, which is what actually provides the pain relief. Now, because of genetic variations, some people are ultra-rapid metabolizers. Their CYP2D6 enzyme works overtime. They convert codeine to morphine really, really fast. This can lead to dangerously high morphine levels, risking side effects like severe drowsiness or even slowed breathing.
Wow, that's actually terrifying. You're giving something you think will help ease pain, but because of their genetics, it could potentially be harmful. Especially scary thinking about giving that to a child.
Exactly. And then you have the opposite situation. Poor metabolizers. Their CYP2D6 enzyme barely works at all when it comes to codeine. So for them, taking codeine results in very little, if any, morphine being produced. The painkiller essentially has no effect. Imagine that frustration giving your child or your elderly mom something for their pain, hoping for relief, and just nothing changes. You feel helpless. It's not the drug itself that's bad, maybe. It's just not right for their specific genetic makeup.
That makes so much sense of experiences people have. It's not about not caring enough. That's a biological mismatch. What about something like ibuprofen? That seems even more common.
Ibuprofen is another good one. It's mainly processed by an enzyme linked to the CYP2C9 gene. Now, if you have certain variants in that gene, it can slow down how quickly your body clears ibuprofen. So the drug hangs around longer, which increases the risk of side effects like stomach bleeding or kidney issues. And if someone's already in pain, adding stomach problems is the last thing you want.
Right. And paracetamol, often the first thing people reach for, especially for kids. Any genetic influence there?
Yes, even paracetamol can be influenced, though it's generally considered very safe at the right dose. There's a gene called UGT1A1 involved in its metabolism. Certain variations might affect how efficiently it's processed, potentially increasing the risk of liver toxicity, particularly if doses are too high or taken too frequently. Again, it's about subtle variations potentially impacting safety or effectiveness, which is crucial when you're caring for someone vulnerable.
So, bringing this all together, the core idea is that two people can take the exact same pill, same dose, but have completely different results purely because of their genes. It really explains why finding the right pain relief can feel like such a frustrating game of trial and error, trying one thing, hoping it works, then having to switch.
That's the heart of the problem, isn't it? And that trial and error process is so much more stressful when it's for someone you love who's suffering. All that guessing, the waiting, seeing them still in pain, it causes a lot of anxiety for everyone involved. It can delay finding something that actually works and just makes the whole situation harder.
Okay, so how does pharmacogenomics PGX actually help us move past this guessing game? How does it lead to, a more reliable approach, especially for families dealing with ongoing pain?
Well, instead of just trying things blindly, PGX gives you information up front. Think of it like getting a personalized weather forecast for how someone is likely to react to certain drugs. It can flag which painkillers might work well, which might not work at all, and importantly, which ones might carry a higher risk of side effects for that specific person. This means you and the doctor can make a more informed choice from the start. Less guesswork, less waiting, less potential for adverse effects. It's about getting to effective relief faster and safer.
That sounds incredibly valuable, shifting from hoping to knowing, almost. So how does someone get this information? What is PGX testing actually like?
It's usually quite simple, actually. Pharmacogenomic testing typically just involves collecting a DNA sample, often from a cheek swab, just rubbing a cotton swab inside the cheek, or sometimes a blood sample. That sample is then analyzed to look at specific genes known to influence drug response. The results come back in a report that maps out those potential drug-gene interactions for various medications, including common painkillers.
So it's not just generic advice. It's tailored specifically to that person, your child, your parent. What are the real practical benefits of having that PGX profile when you're trying to manage pain for a loved one?
The benefits are pretty clear, I think. Firstly, reducing the risk of harmful side effects. That peace of mind alone is huge for any caregiver. Secondly, it increases the chance of picking a treatment that actually works the first time. Less trial and error means faster relief. And thirdly, it builds confidence. Knowing the choice is based on their specific biology helps everyone feel more secure about the treatment plan, especially if it's for managing chronic pain long term. There are services becoming available now, like Pro.Genome from Alpro is one example, that provide these kinds of insights for everyday medicines, giving a clearer guide for doctors and patients.
Right. So recapping our deep dive then, the way a painkiller works or doesn't work isn't just random. It's deeply connected to our individual genetic code. Pharmacogenomics helps us read that code. Especially when you're trying to find relief for someone you care about, understanding this can make a huge difference.
Absolutely. It helps shift the approach from reactive trial and error to something more proactive, personalized, and ultimately safer and more effective.
So the next time you reach for that painkiller for yourself or for a loved one, and maybe the result isn't quite what you expected, remember this conversation. It might not just be chance, it could be their unique genetics at play. And that's where tools like PGX testing can really help, turning that uncertainty into useful information, giving you more confidence, and hopefully providing better relief for the people you look after. And just this final thought to leave you with, if our genes hold these kinds of clues for something as common as painkillers, well, what other areas of medicine and health might be completely transformed when we start looking through this personalized genetic lens? Something to think about.